Gentlemen, welcome back for Unit 6. Today we're going to be talking about integration and accumulation of change. Once again, for those of you following along in terms of percentages, I want to emphasize once again this is going to be a larger percentage of the test. Your topics are listed here, and you should either have that in front of you. And what are we going to be emphasizing? Well, we're going to be talking about Riemann sums. Which again is going to be RRAM, LRAM, MRAM, and also being able to convert them to your definite integral notations, etc., and accumulating areas. So we'll also get into a few more techniques, but let's get started on the Riemann sums. To get going on this, LRAM, of course, means we're getting our height of our rectangle from the left-hand side. Here we're getting it from the right-hand side, and here we're getting it from the midpoint. But the key thing to remember is all of these are going to be rectangles as we're doing it, which is just going to be a simple base times height. Whereas the bottom one, we're looking at trapezoids. Please remember what the formula would be for a trapezoid, where we're going to be saying that we have something like this, base 1 plus base 2 times the height. Though when we do it, it ends up being more, we kind of flip-flop these for a second, and we end up saying that this is going to be height 1 and height 2, and here is the distance between the two columns. So let's get started on this, and we're going to be estimating this using 4 subintervals. Now, fortunately, the data we've been given kind of leads us to be doing the 4 subintervals. Here's interval 1, here's interval 2, interval 3, and interval 4. I'm asked to use the RRAM, which means I'm going to be using the height on the right-hand side, which means I'm going to be using 2, 3, 2, and 5. And when I write it out, I'm going to start off with, well, what is the distance between these first two here? Well, that's 2. And then I use my height of 2 there. Again, the distance between these two in here is going to be 1. And I use my height on the right-hand side, which is 3. And then we're going to say, okay, how about my distance between 3 and 6? And I'm going to say my height is then 2. So I'm going to say 3 times 2. And then finally, we're going to finish off this one by saying we're going from 4 to 10, which is a distance of 4. And I'm going to use that height of 5. So I'm going to be looking at 4 plus 3 plus 6 plus 20, which is going to get me a grand total of 33 is my answer there. Okay, next, you're asked to do this same problem using trapezoids with 2 subintervals. Now, if I'm only going to use 2 subintervals, I'm going to try and do it the easiest way possible. And in this case, that's just going to mean I'll use from here to here and here to there. It's going to be using the data set, try and cut it up evenly. So I'm going to say, all right, 1/2, and I'm going to use my heights. I'm using 1 and 3 because those are the heights on that side, and the distance between the two x coordinates is 3. And then we do the same thing here, and this time we're going to say we've got 1/2. I'm going to say my height is 3 on that, and my height is 5 there, and the distance between these two is 7. Okay, so no big deal on that, just do your computation. So I'm looking at 1/2 of 4 times 3, which is going to be 6. And then 1/2 of, let's see, I've got 3 plus 5, which is 8. 1/2 of that is 4. 4 times 7 gets me 28. So I'm looking at an estimated value of 34 there. Okay, moving on. Next, I'm using this information here, and again, assuming that this year's test, AP is going to do what they can to try and reduce the opportunity for you to be able to do stuff using calculators and computers. The previous slide was a great example of one way. Here's another, where they give you a graph, and you have to interpret the graph and try and handle that sort of thing. So we're going to take the information from what they've given and try and come up with something. They say, I want to integrate that space in there. And you're going, well, that's not too hard. I just know I'm starting here and I'm going to there. So that's the space I'm looking at. And also, please note that I'm going to have two sub-intervals. Well, that's not too bad because I can kind of say, yeah, doesn't surprise me. I've got one going from here to there and one going from there to there. That kind of makes some sense. The only thing I need to do is I need to figure out, well, which technique did I use to get the answers that I'm looking at here? So let's take a quick crack at this one and say, well, it says I'm looking at 5 times 2. Well, I can say that my distance from here to here is 2, so I've got that. And then I'm going to be looking up here and say, that's my height. My height is on the right-hand side, so I'm already leading towards RRAM. Let me check it again using the next one. My distance from here to there is going to be 3, which matches up nicely. And the height on the right-hand side, yes, is going to be 2. So I'm going to say I'm using the RRAM technique to come up with that approximation. Okay, so far so good. Next, you're looking then to do this one and talk about things where you're doing the whole distance between 0 and 9, but I'm using 4 subintervals. Okay, and again, I get the 4 subintervals from that. So I've got one subinterval looking like this. I've got another one in here. I've got another one in there. And I've got a final one in there. Okay, not too difficult. So let's see what we've got here. Now, I'd agree that on my first subinterval, I'm looking at the distance between my values is going to be 3. And I'm looking, where do I have a height of 5? Well, that's over here on the left. Let's confirm this and make sure that what I've assumed to be now an LRAM technique is right. So I'm going to go next into this one. I'm going to say my distance from 3 to 4 is 1. And I check my height, and my height here is 2. Yeah, I've kind of confirmed it. I've got this being an LRAM technique. And once again, if you don't believe it, you can check other points and make sure that everything is going okay on that. And you can see that, yes, if I check my other points, I do have a height of 3 on that one, and I have a height of 6 on my other left-hand side technique. So I just proved that one down nicely. Next up, it says the table below gives velocity values in feet per second every 30 seconds, and you're asked to once again determine what type of technique or what sort of approximation technique are you using on this. Now, again, these are nice and easy because to go from 0 to 6, the obvious one would be to use 2 subintervals there, and all we need to do is work with this, and whoops, no idea why it did that, but there we go. Okay, that's odd. All right, so we're now going to say, okay, I've got my height being here as 10, and the distance between these two is 3, and my height here is going to be 15, and the distance between these two is 3. Now again, it's 15, even though I was given negative 15, but notice it's the absolute value, so I'm going to say that this is an LRAM situation. Okay, coming back and taking a look this time from 0 to 6, same sort of problem, except that they're not actually using anything from the chart. So we're going to have to kind of fake our way through this and see if we get the information we're looking for. They start off by saying, well, you've got a distance. They're using a common distance of 2 in each of these examples to get your 3 subintervals to cover the distance from 0 to 6. Okay, but it's saying, well, I'm going to get my height first from 0, then from f of 2, then from f of 4. Notice, once again, this is LRAM because it would be the left-hand side if I was to draw these figures. Okay, major questions I'm hoping you don't have at this point. Let's keep moving on. Okay, what I would like you to do is take a look at this And basically what I'm going to want you to do in each of these cases is compare column A and column B and figure out which one is going to be bigger. And then see if you can come up with a reason why. Okay, and I would say pause this and see if you can come up with the answer, and then turn it back on because I will give you the answer. Going once, going twice. Okay, here we go. Number one, given what I've got here, it says you're going to try and use a right Riemann sum, which would mean something that looks like this. Now, clearly, that is going to be an overestimate. Okay, my right Riemann sum is going to be an overestimate. And then I'm going to look at a trapezoidal sum here. And I'm going to just make one giant trapezoid because it's super easy to draw that. And this one, take a look, folks, it is an underestimate. Okay, so if I've got the right Riemann sum overestimating, and I've got the trapezoidal sum underestimating, I'm hoping that everybody would agree that I'm going to have column A has to be greater since I have that situation. Next up, go to the second one down and see if you can figure out which one is going to be greater, column A or column B. Give it your best guess. And I'm assuming you're back, having come up with something. Well, I'm going to compare things again. This time I'm looking at a right Riemann sum here, and that's going to be something like this. Okay, that's definitely going to underestimate. So I'm going to say RAM is going to underestimate. And I'm probably going to also, in my own mind, going to underestimate it big time. But we're also going to be talking about the actual integral here, it looks like. So I'm going from B to A. Well, we've got something that's fairly straightforward on that. Clearly, we compare that to the actual area, and I'm going to say, well, that is the function that describes the actual area. So clearly, B is going to be my answer on that because it's much bigger. Okay, next up, move on to this one. Give yourself a second, compare these, and see if you can explain why. Once again, pausing after you've come up with your best guess. And we're back, and now we're going to say that, okay, what have we got here? Trapezoidal sum with 3 equal subintervals and trapezoidal sum with 6 equal subintervals. Now, again, when you've got a trapezoidal, okay, and when you've got a trapezoidal, all we need to do is we need to compare what's happening. Now, I'm going to go back a couple slides because I kind of skipped through that too quickly. But I'm going to say, when do you know when things under and overestimate? Well, with LRAM, again, an LRAM function, if you are increasing as opposed to decreasing, for many of you, if you don't remember this, do a quick sketch. If I've got a function that's increasing and I'm using LRAM, that means it's going to underestimate what is there. Whereas if it is decreasing, let me switch that back. If I have a function that is decreasing and I use the LRAM technique, that one is going to overestimate. This time we're going to go with RAM, same sort of thing. And when in doubt, just do a quick sketch. It takes a couple seconds. The RAM, when it is increasing, is going to overestimate. And when it is decreasing, once again, this one is going to underestimate. Now, in terms of MRAM, it pretty much varies. This tends to be one of those ones that's a little bit more, you got to judge it by eye. But the trapezoidal, we're not as interested in whether or not something is increasing or decreasing as much as we are concerned about concavity. We're looking, is it concave up or is it concave down? And so what I'm going to say on this is, take a look. I've got a concave up, and here I've got a concave down. Actually, you know what? Let's just draw them both as increasing functions, and you'll get a chance to see. If I draw a trapezoidal approximation here with just one trapezoid, you can see that this one will overestimate it. But for concave down, you're looking at something that will underestimate it. Okay? All right, back into this problem here. Okay? And here we go. Now I've got a trapezoidal sum, and I know that what's going to end up happening on this is in both cases they are going to overestimate. But, okay, both of them will be overestimating. However, you're asked to determine which one is going to be greater. And the reason why I'm going to go with column B on this is because, I'm sorry, not column B, column A on this. I would say column B is going to be more accurate, but because I only have 3 subintervals, that means that I'm going to get more overestimation. It's going to be over by a larger amount, because remember, one of the rules when you're using the LRAM and RRAM and trapezoidal techniques is the larger number of subintervals, the more accurate it becomes. Okay, please take a second and compare the second one down here, where we're comparing the trapezoidal sum and the left Riemann sum. Okay, and I'm going to call time again, and I'll say, well, your trapezoidal sum will overestimate. I'd agree. And the left Riemann sum will overestimate. But the thing that we're looking at is which one is overestimating by more. And you can say that it's pretty clear that what I've got in there in green is going to be bigger. So I'm going to say that my left Riemann sum is going to overestimate by more. Okay. And next up, let's take a look at this one at the bottom. Okay, and once again, we've got right Riemann sum with 3 subintervals and right Riemann sum with 6 subintervals. Okay, once again, both of these, since it's an increasing function, are going to overestimate. But because you have 6 subintervals here as opposed to 3 subintervals here, column B is going to be more accurate. So therefore, column A will be the greater value. Okay, give it a second. And moving on. Next, this is kind of the generic rule for Riemann sum notation. You will need to assume that they will come up with at least one of these problems in the multiple choice. Now, the challenging question on this one is, what could you do to potentially change this so that it ends up being LRAM as opposed to RRAM? Okay, now for those of you that had good teachers that when you did your summation stuff last year, that things made sense, this should be not too bad. On the other hand, for those of you that barely survived summation notation, you're going to strap on, because this one's going to be a little bit more challenging. Now, what I want you guys to do is, please note, here's my f of expression. And what I'm doing is it's saying that I'm starting at A, which is here. There's my starting spot, and I'm hoping people are okay with that. But notice it doesn't actually start at A. It starts at A plus all of this stuff in here. That is stuff that's been added. That's stuff to the right of A. So because it's stuff that's been added to A, so I didn't actually start at A, I'm going to be starting a little bit to the right of A. We're going to say that this ends up being an RRAM approximation. So what do you do to knock this thing down so that you don't start to the right, so that you would start to the left? Okay, the key is to look in your sigma notation. And again, remember what the sigma notation is. That's this stuff in here. This phrase tells you where to start, and it tells you where you're going to. Well, since I'm going up to infinity up here, I really don't need to worry about that, and I really can't change anything there. But the problem is that by starting my k at 1, that means that I've added in one of these to begin with. So what could I do to knock this down? Well, very simply, what I could do is instead of starting at k equals 1, I could start it at k equals 0. Have the exact same expression, except started at k equals 0. On the other hand, if AP chose to give this to you as a multiple choice question and they didn't give that as the answer, what else could I have done? Well, I could still have my limit expression stay identical to what they've given me to begin with, but what could I, or how could I modify what I've got here so that I am not going to be starting to the right of A? And how I'm going to do that is I'm going to actually start at k minus 1. And then the rest of it is going to look exactly the same as what's here, because by starting it where I've got with my k minus 1 in that part, I get myself back down to 0. Okay, now, this again is by far would be a ridiculously difficult question. Do I think that AP might decide to throw something at that? Probably, because they're anticipating that people are going to be bending the rules to the best of their ability on this test. And this is one way that they can really stretch things. I'm hoping they don't, but that would be how you would answer something like this. Okay. On the other hand, this is a much more straightforward question. All we have to do is use the basic expression that I've got up in here, and just remember that your rules have to do with this. You're going to be saying, to the best of your ability, whenever you're doing one of these problems, I'm going to start off with, and again, you might remember that when we did this problem, we kind of had a delta x concept of being b minus a all over n, and my actual x values started off being a plus delta x times k. So basically what you need to do is you're always going to start off by saying take b minus a and put that over n in here. That's going to go outside, and it's also going to be duplicated in here. And then your a value is going to have to be rewritten in like that, unless a is 0. So let's take a second and take a look at this one and see if you can come up with the expression there. Okay, so when it comes to writing this, I'm going to cheat and do as little work as is possible, because these things always intimidate me anyway. So I'm going to say, okay, I've got 5 and 3. So it's going to be 5 minus 3 over n. I should be seeing 2n popping up once inside the parentheses and once outside the parentheses. Nope, nope, nope. Yep, that's the only one. Okay, potentially, yeah. Does it make sense? Are we being logical here? Does that work for people? I hope so. Double check it and make sure, did I get my a value in place? Yes, I did. So we should be good to go on that one. Any quick questions anybody's got? I hope not. We're just going to keep moving onward. Okay, please take a look at this one. And again, pause this if you need to. This is going to be a multiple choice. Figure out which one is going to apply to what one. Once again, please feel free to pause this, because I'm going to keep moving onwards. And here we go. Let's take a crack at this, and I'm going to look and see how do I get things to line up. I'm going to start off by saying, oh, 3 and 0. So 3 minus 0, that's going to get me, this one right in here. Both of those are going to be very nice. And the only reason I don't have an initial value is because, well, my initial value is 0 on that. So I can immediately just back this thing up and say, I've got 3 over n, I've got 3 over n. So that means I'm looking at A on that. Next, change colors and change problems. Looking at 1 and 2. So I've got a difference between those two of 1. So I'm going to say I've got 2 minus 1 over n. So let's see, 1 over n. So I should be seeing something with 1 over n somewhere in there. Oh no, I've got a 1 over n here, and I've got kind of a 1 over n in there. So I'm looking at B on this one. Okay. Next, let's move on to this here. Let's say I've got 2, 6, and 2. Difference there is 4. So I'm looking at, ooh, got that, got that. So that's going to be C. And then finally, let's just finish up and say 1 minus negative 1 is going to get me 2 over n. So I've got 2 over n, and I've got 2 over n. So I'm looking at D, hoping that that makes sense. Next up, same sort of thing in here. What do I need to do, or what do I need to come up with on this? Okay, remember that it's going to be A plus what your change in A value is times K is going to be the thing that's going to go in that box. So in the case of this problem, my A value is 2. So I say I've got that. Plus, what is my change in A? So I'm going to say 9 minus 2 over n times K. So I'm looking at my final answer being 2 plus 7k over n. Okay. Now take a look at the second one. This one takes a little bit more thought because we actually have to substitute it into a function here. So please be careful as you're doing that. Okay. Same sort of setup as we're doing this. Okay. How do I come up with this, and how am I supposed to come up with a way to write it? Well, just because I've got that f of x, I know that that f of x has to go inside of my expression. Okay, and because I've got that f of x, I'm going to be subbing in for that x in there. So let's take a shot at seeing what's going to have to go in there. It's the same setup as what I've got here, though. So I'm going to say we've got negative 2 plus, the difference between these two is 5k over n. And now that is going to go in for x in there. So my final expression in my box is going to be the sine of 4 times, and I'm just going to leave this as is. And my guess is AP would do the exact same thing. Now again, notice I can double check to make sure that I did things correctly, just like I did here. That's 5 over n, just like that's 5 over n, and here this is 7 over n, and that's 7 over n, which is a nice way of confirming things. All right, next up, we're going to be doing areas. So we're going to use geometry to evaluate the integrals. And again, I realize for some of you, geometry was a long time ago and maybe not your favorite place to live, but we still need to go there on this. So let's see what we can come up with about finding the areas of each of these. Okay. All right, moving on. First one. I'm going to start off in purple, and I'm going to say, how do I find that? Well, it's going to be the area from here to there. Now, you can cut it into a rectangle and a triangle and do it that way. Still going to get the same answer. But I want you guys to be able to practice a trapezoid, because I'm assuming trapezoidal rule may show up when you're doing approximation for Riemann sums. So anything I can do to encourage that is a positive in my book. So here we go. 1/2. And I'm going to say, what are my heights here? Well, my height here is 2, and my height here is 4. And the distance between these two is 3. So I'm just looking at 9 for that one. So I have an area of 9. Next up, I'm going to do that one in Oh, let's go with green. And the way to do this one is to pretty much say, all right, I want to find this area, which is going to be the green box with a semicircle cut out of it. Well, what's the area of my green box? Well, that's going to be, let's see, that's 3 to 9, which is 6 by 4. So I'm going to say 6 times 4, but I need to cut out this area in here. Now this circle has a radius of 3, so it's going to be 1/2 pi times the radius, which is 3 squared. And so I end up with a final expression of 24 minus 9/2 pi. Okay. Hopefully that all went fairly quickly and easily. Now let's take a look at the last one. And I'm going to cut this piece off here so it's not making a mess. It's asking me to find the area between 10 and 14, which is here. So my problem is this section is above and this section is below. So all I need to do is add those, but the section that it's below, I'm going to subtract. So I'm now looking at 2 times 4 minus my negative area, which is 2 times 2. Hopefully that's pretty easy to get you an answer of 4. Going once, going twice. Anybody with anything? All right, here we go. Next up, fundamental theorem of calculus. Again, rushing through. Hopefully you guys all remember, I need to have 3 things going on. Number 1, I need to have the derivative of an integral, or the integral of a derivative. I need to have like d dx of this, or I could have something like that. In either case, 2 things that undo each other. That's step number 1. Got it. Step number 2 is you need to have a constant as your lower limit. Okay, and once again, cool on that. Third thing is the top one has to be in terms of whatever your derivative is. So if it's d dx, it's going to have to be in terms of x. Doesn't have to be x by itself, but it definitely makes things easier, which is exactly why they probably won't do it. So let's work through this first one. I'm going to say, yes, I have the derivative of an integral. Check. Yes, my lower value is a constant. Awesome. And yes, this is in terms of x, as is that. So I can just use my fundamental theorem of calculus rule, which is to immediately take this, sub it into there, but then take the derivative of it outside. So I'm now looking at 2 times 3x plus 3, and the derivative of 3x is going to be 3. So I'm now looking at 6x plus 3 times 3, which is 18x plus 9. Woohoo, we got straight to our answer. Okay. On the other hand, looking at this one, I'm going to say, yes, derivative of an integral. Cool there. Lower limit, not in the right place. What do I need to do? Flip things over. So we're now looking at this expression. I've changed it up slightly. I flipped it. Can I flip it legally? Yes, but what do I need to make sure that I do when I flip it? You need to throw a negative. Anytime you flipped your top and bottom, you need to throw a negative out front. Okay, and now things match up. We've got the lower bound, and I can sub in my value for x. So I'm now looking at 2x quantity squared plus 2 times 2x, but the whole thing must be with a negative. Okay, so I'm now looking at 4x squared plus 4x, and I now need to distribute that negative there. So let's see what we can do on that. Oh, wait a second. I can't believe I missed that. I did the substitution, and what did I forget? I forgot to put the derivative of that there. Shame on me. All right, so we're now going to say that this is going to get me a negative 8x squared plus 8x. Okay, should be okay with that. I'm hoping. Okay, everybody should be okay on that. If you've got a question, that's definitely going to be you can hit me up a little bit later on, and I will see what I can do about hopefully being conscious enough to be able to respond to people's questions. So yeah, and I forgot to distribute the negative here. So there you go on that. Still working. All right. Now, this should look familiar because I'll be honest, we did something like this back on our chapter stuff. So I'm hoping that people are still okay on this. Please see what you can do on this one. Okay, please see what you can do on this one. Okay, and pause if you need more time. And let's keep going on this. First off, you've got this function. It says that I am starting at -3. So I'm going to start at -3. Everything I do is going to be based off of that. Okay, now let's see what we can do here. Going once, going twice. All right, g of 1, which tells me I need to find the area here and the area there. Now, fortunately, these two things just cancel each other out because we're looking at same base, same height. It's just one's above and one is below the x-axis, so I end up getting 0. Next up, let's make that go away, and we're going to now work on this part in here. Got it. No problems on this. It's going to be just 1/2. Base is 2, height is 4, and so I'm going to be looking at 4, right? Or am I? What's wrong with this? Wait a second. How come I can't just say it's 4? Remember, one thing is wrong there, and make sure you're very careful when you look at this. I went backwards. I went in the wrong direction. I'm always talking about from -3 to x, and we're assuming things are going to go to the right. Because I went backwards, instead of being a +4, that's going to make that into a -4. Okay? All right, make this go away again, and let's take a look at the next one. What is g prime of -2? Well, again, I'm just going to look at my function at -2. I'm looking there. What are they asking me to do? Well, if you need a little bit of a brush up on this, remember g of x was given to be this in here. And then I'm looking for g prime. Now my g prime is just going to be d dx of this expression here. And wait, that's the fundamental theorem of calculus, so that's just going to get me what is f of x on that. So I'm going to just say, well, what is f of -2? And I'm hoping people immediately say, I'm looking at a value of 2, and we're good. Next, same sort of thing we're looking at 1, and we're going to say, well, what is f of 1? I'm looking down here, and I'm looking at -4. And then finally, g double prime. Well, hopefully people don't have that much of an issue when I say, well, if I'm looking for g double prime of x, all I need to do is take the derivative of f of x. So I'm looking at f prime of x, and f prime of x at -5 is basically saying, what's my slope there? Well, my slope there is going to be 2. Okay, still rolling. Here we go again. Next, same sort of graph, except this time we're trying to go through and do all of these questions. I would encourage you once again to please pause this and work through it, or at least get through it, because just listening to me talk doesn't necessarily help you a ton. All right, on what interval is g of x increasing? Okay, so I am now going to state that once again, I am starting here. And where am I adding area? Well, I would definitely say I'm adding area from -3 to 1. But again, overall, what happens? Well, let's go backwards for a second and say that on the graph, because as I go, and this is overall when they're asking this, when is g of x increasing? It's just saying, as I go from left to right, where am I adding area? Even though I would get, and you remember from the previous problem, I got like -4 at -5, I'm going to end up adding area there. So it's actually going to be from -5 to -1 on that, because I am adding area as I go from left to right. Hopefully that makes sense. All right, next, let's take a shot at when is g of x concave down. Now remember, when they're asking about g of x, that means I'm looking at g double prime of x. When is that going to be less than 0? So when is g double prime going to be less than 0? I'm going to look at my graph and I'm going to say, well, that's when f prime of x is less than 0. In other words, when are my slopes negative? And there's going to be two areas. And once again, hoping that you recognize straight away that section in there and also this section in here. So when it comes to writing this out, we're going to go from -3 to 1, and then again from 3 to 5. Okay, next, when do I get to my maximum value? Okay, now we're overall the maximum value of g. We go back to our definition up here. When I'm going to the left of -3, I'm getting negative values. So clearly it's not going to be anything that's to the left of here. It's going to be that section where I've added values. And so in this case, I'm going to say, well, I've got my maximum value at -1. Well, what is that maximum value going to be? Well, that's the accumulated area from there to there, which is going to be 1/2 my base, which is 2, times my height, which is 4, which is going to get me a maximum area or a maximum value of 4. And next, we're going to be talking about our minimum value. Now, I have two different ways that I have to consider two different areas. So I would say I am going to be having a minimum value when I get back in here. Now, again, remembering we actually did this problem already on the previous slide. We ended up saying that that value, or g of -5, got me -4. Now, what other areas are in contention for having maximum area? Well, I'm going to just say that, remember that at 1, we had gotten back to an area of 0, and then we continued to go this way, so I ended up getting all of this sort of negative area in there. So if I could figure out what the area is for 5, that would be worthy of consideration also. So again, remembering that this area in here and this area in here, they cancel each other out. Right now, I just need to find the area of this stuff up in here. Okay, and well, for the sake of time, I'm going to say that this is going to be 1, 2, 3, 4, and this is going to be 1, 2, 3, 4. So I'm looking at 16. And then I need to, okay, 16. And then I need to cut out this shape in here, which is a semicircle. And we're going to say that that's going to be pi r squared, my radius being 2. So this time I'm looking at 16 minus 2 pi. Now, in terms of what I've got on that, I'll be honest, you're probably going to want to use a calculator to actually do that. I don't think that AP would choose to throw that sort of thing at you, except on the calculator section. So you're going to say that that area that's underneath would be 16 minus 2 pi, which ends up being 9 point something. But remember, it's underneath. So this whole thing ends up having to be negative because it's underneath. And it ends up being 9.71. So I'm going to say it achieves its maximum value here at 5, and its maximum value ends up being 16, or not 16 minus 2 pi, 2 pi minus 16, because when I distribute that negative, you get that. All right, still rolling. Here we go. Next, when does g of x have a point of inflection? What am I looking for there? Again, remember that by definition, we're looking for when g prime of x or g double prime of x changes signs. And again, where am I going to find g double prime of x? I get that from f prime of x. So I'm looking at the locations where my slope of the expression up here changes signs. So I'm going to say I've got one here at 3. I've got one here at 1. My slope changes from, at -3, it changes from positive to negative. Then at 1, it changes from negative to positive. And then again at 3. So I'm now looking at, going to be at 3, 1, and 3 are going to be my points of inflection. Okay, still rolling. Here we go next. Selected values of the twice differentiable function as derivative f prime are given in the table. What is the value of this? Okay, now we're going to go to the first fundamental theorem of calculus part 2. How do you go about doing that? Well, remember, this is an integral, this is a derivative, okay? So what does that mean? Hopefully you guys remember that I can take the integral of each of these and I end up saying that that's going to be f of 6 minus f of 0. Well, f of 6 is going to get me 2. F of 0 is going to be a negative 22. And so I'm going to be looking at 24. Okay, questions? I hope not. Again, remember that by definition, what you're looking at here is you're going to say that unlike the indefinite integral, to find something where you've got a definite integral, all you need to do is take the integral of the function, and it's the integral of a derivative, so that's how I get down to f of x, and then I sub in my values. So it kind of ends up looking like this, where you're going to say, oh, that's just going to be f of x, and all I need to do is sub in 0 and 6. Okay, next up, let f be a differentiable function so that f of 3, and you've got this loveliness. Okay, well, let's see. If I'm trying to find this value, how are they writing it this way, or why are they writing it this way? They're saying, I know that my value is there, and I'm trying to find f of 5. So what I can say is I can integrate from my known value, which is 3, up to 5 of f prime of x dx there, which hopefully is not too earth-shattering. And then I just add the initial value, which is f of 3. So when it comes to doing the actual hard work, we're going to say, well, we're going from 3 to 5 of the natural log of x squared plus 1 dx plus the 2.2345 thing. Okay, now, how can you do this? Let's, for the sake of argument, say, well, that's going to be 1 over x squared plus 1 times the derivative of the inner function, which is going to be 2x there. And then I substitute in from 5 to 3 plus, we were looking at, what was it, 2.345. Now, I'll be honest, at this point, I'm just going to put things into the calculator and say my answer ends up being 7.976, okay? It's probably one where, forgive me, I would not be terribly surprised if this portion was done on the calculator, and then all you really need to do is remember your keystrokes in order to enter that into your calculator. Okay, and by the way, notice that there's this calculator symbol up here, which tells you that it would be a calculator problem. So this is completely unnecessary. Okay, next up, what else do I have now? Integration techniques. Okay, we've got just a couple here, and I know we're starting to get short on time, but let's see what we can do. Kind of the tops are the ones that you memorized. Okay, those of you that were in class on Thursday and Friday, I handed out a sheet. If you've not gotten that sheet, somebody please send me an email to remind me. It's a nice list of things you should have memorized for the AP test. They're fairly straightforward. What are other things you might want to touch up on? U-Substitution. U-Substitution will be part of the AP test. Expect it. And forgive me, but as much as I want to say that, yes, this test is strictly about calculus, no. They are going to test you on, can you demonstrate how to do the technique? It will not be just a problem where you just do a U-sub. They're going to ask you to get halfway through it. So if you don't like U-bounds, I don't care. Brush up on it, because otherwise you're going to miss the problem, because they almost always tend to ask that as a U-bounds problem. All right, and next one, I would say, kind of last one is long division, which hopefully you're remembering, or when we get done with it, you will remember. Okay, moving on. Next up, what are your known integrals? How do we go about doing this? Do you remember? I hope you do. If not, honestly, it should be something where it's just going to be brush up on things, okay? What do I need to do? How do I do this sort of thing? Well, remember, what is the a sub nth? Okay, how do you go about doing that sort of thing? Let me pause this for just a second. And let's fire this thing up again. Ready, set. I'm looking at this is going to be to increase this power by 1, so that's going to be n plus 1 over n plus 1 there. Next, the integral of sine, notice not the derivative, the integral of sine would be a negative cosine of x, because remember, when I take the derivative of this, that's how I get sine x. And then we're going to look at the integral of cosine is going to get me sine. And let's see what else here. Okay, e to the x, oh, we love that. It's going to be so easy. Okay, we've got that. Then secant tangent, oh, that's just secant x. Secant squared x is going to get me tangent x. By the way, please remember, since I don't have any sort of values and numbers, all of these would have a plus c. Oh, yeah. And anyway, keep rolling on this. 1 over x. I'm hoping that people remember that that's the natural log of x. I'm going to skip that one. This one's going to be cosecant x. And then our inverse trig ones that everybody forgets, but I definitely say you should make sure you study this at least the night before. Again, plus c, and this is going to be sine of x there. Again, brush up on these things, folks. Hopefully it will work. All right, next up, changing gears. We're going to go for U-substitution on this. How do you know that you're going to have something that's U-substitution? Again, remember what we've got is that U-sub is just a fancy way of undoing the chain rule. So anytime you think that a chain rule has been done, probably you're going to use a U-sub to help you to get undoing this. And again, we kind of tend to emphasize what is my inner function, and we use that to identify what we're going to have as our u. I'd say that that is my inner function on this one, so I'm going to say that my u is going to be x cubed plus 1. So I'm saying du is going to be 3x squared, and then dx. Now, I now need to see if I can match this up with what I've got here for the rest of this. And I'm going to say, yeah, I've got the x squared and the dx, which matches up with this. So what do I need to do? I'm going to rewrite this so I'm looking at 1/3 du equals x squared dx. So now when I rewrite this in terms of u, in the place of x squared dx, I'm going to put 1/3 and du. And then in the place of the x cubed plus 1 to the 4th, I'm just going to make it u to the 4th. And we put my integral symbol there. So when I integrate that, I've still got my 1/3 heading out front, so that's going to be u to the 5th over 5, or we're going to end up with my expression, sorry, I took an integral and I should put my plus c, so u to the 5th over 15 plus c. Next up, see what we've got now. This one's going to be a little bit more of a challenge. I'm hoping that people pretty easily recognize at this point, hey, there's my inner function. So I'm going to work with that and say that I'm looking at u equals x squared plus 5x plus 1. And so my du will be 2x plus 5 dx. And fortunately, that matches up really, really nicely with what I've got here. And all I need to do is be careful when I'm writing my expression. So du takes the place of this. So there's my du. And then how do I write my substitution? Well, it's going to be u, but remember I've got a square root, but the square root's in the denominator. So that's going to be u to the negative 1/2. Oh, now let's increase my power by 1, u to the 1/2, and then divide by that new power, which is going to be dividing 1/2, which is the same thing as multiplying through by 2, and I've got that, except that, oh wait, and that's the thing I forgot to do on that last one. Dang it, I got lazy. I forgot to sub back in. So x cubed plus 1 over 15 plus c, and I'm going to raise that to the 5th power. Same thing here, I need to make sure I sub in my expression. And so I'm looking at 2 times the square root of x squared plus 5x plus 1 plus c. Okay? All right, next up, I would say on this, see what you can do on your own, see what you can do. Okay, paused. Please understand, I would like you to, if you're looking to maximize your score, please be comfortable with u-bounds. Once again, my inner function is just going to be x squared plus 1. So I'm looking at du equals 2x dx. Once again, trying to match what I've got up top there. So I'm looking at 1/2 du equals x dx. So when it comes to rewriting this, I'm going to say du 1/2, and in the place I'm just going to put u, except that I'm not going to put it down below. I'm going to make it -3 there. Next up, what am I going to do on this? Well, I'm going to integrate both of these, and oh wait, I still have the bounds to deal with. Now, how do I find my u-bounds? All I'm going to do is I'm going to substitute my actual bounds into my equation for u. So that means that finding u of 2 just means substituting the 2 in for x. So I'm looking at 2 squared plus 1, which is going to get you 5, and I'm looking at 0, which is going to get you 0 squared plus 1, which is going to be 1. So now I've got this. Now, I would expect AP on a multiple choice question to have this be the answer. Well, it's only one problem. Yeah, I know, but I'd hate for you to miss out on the grade you want by doing something small. Please just be able to do this, all right? So back into this, going through the process of doing this, you're just going to say, okay, I'm going to decrease my power by 1, and now I'm going to divide by that new power, and then I'm going to sub in my new limits. So since this is just going to be a -1/4 when I multiply this stuff together, and then I'm going to say, well, 5 to the -2nd is 1 over 25, and 1 to the -2nd is going to be 1. I'm now looking at this expression, which is 1 minus 4, And so that's going to be, what, a negative 24/25, which is going to get you 6/25 as a final answer there. Okay, again, not incredibly intimidating, but definitely a make sure you're aware on how to do that. Okay, one more, pause this, see what you can do on this. And we are back in business. So I'm looking at my inner function. Again, the inner function sometimes is just the exponent, so that's what I'm going to work with. U equals sine of 2x, and I take the derivative of that once I rewrite this so you can actually read it. And we're going to say du equals, the derivative of sine is cosine 2x, times the derivative of the inner function, which is going to be 2 dx. Now, trying to make things so that they match up nicely with what I was given originally, that there matches up. So next, all we need to do is make it so that this part is all by itself. 1/2 du equals cosine 2x dx. Okay, still rolling on. Next up, I now can do my substitution, and we're going to say that we're going to have now 1/2. I've got du, and I'm going to say e to the u, and there's my integral. Now, fortunately, integrating e to the u, though I wrote it as an x, so shame on me, is very easy. So I'm looking at 1/2 e to the u plus c, except that, oh wait, I still need to substitute in my u value. So I'm looking at 1/2 e to the sine of 2x plus c. Okay, last topic that we're going to cover, long division. So here we go. Ready, set, and I'm going to warn you, this is probably one of the uglier problems that we're going to mess with. Please make sure that you're relatively comfortable with the idea. Remember, all we do with long division is you write out the polynomial that's in the top as your numerator, goes underneath the square root symbol, or not the square root, the division symbol, and make sure you write out all of your powers. If you don't, it's likely to cause issues. So, again, brushing up, what do I need to multiply this by to get that? Well, you're going to say that's going to be just 2x squared. So I take 2x squared times 2x, that's going to be 4x cubed. 2x times 3 is going to get me a positive 6x squared. Now, real briefly, just to remember, you're going to subtract the second one, or as I generally recommend, just add the opposite for, or change the sign for everything, and we're just going to add down. Once again, I'm going to say, what do I need to multiply this by to get that negative 6x? So I'm going to say negative 6x squared is going to get me a negative 3x. And let's see what we've got then. So negative 3x is going to get me a negative 6x squared, and negative 3x times 3 is a negative 9x. Again, and add down. Last step here, I need to say, what do I need to multiply 2x by to get 9x? Well, I'm going to actually add a fraction. I'm going to add 9/2. So I'm going to say 9/2 times 2x, that's going to get me my 9x, and 9/2 times 3 is going to get me, let's see, 27/2. So 27/2, and I'm going to subtract that stuff, and I'm going to end up with a negative 27/2 down here. So now what I've got is minus 27/2, and then remember, this has to go underneath. And now you just integrate this expression here. So not incredibly difficult, but just be a little bit careful. So I'm going to say I'm going to integrate 2x squared minus 3x plus 9/2 minus 27/2 times 1 over 2x plus 3. Okay, well, and dx here. So integrating the 2x squared, increase the power by 1, divide by 3. Increase the power by 1 for this. That's going to get me x squared. I'm looking at 3 halves x squared. Increase the power by 1, so that's going to be 9 halves x. And then we get to this last one. I'm going to leave that negative 27 halves there. And then I need to take the integral of that. Now that would get me the natural log of 2x plus 3. Except that, watch this very carefully. If I integrated this, will I get that? No, because I have that power of 2, or not the power, the coefficient of 2 in front of the x there. So I'm going to need to multiply this through by 2 because I'm kind of undoing the chain rule. It's kind of doing a U-substitution-y type thing, but in short, all I need is this to be 4 here. Okay? Now, this is way harder than I expect you to see. What I'd expect you to see is something more like this. So again, please see if you can do this on your own right now. And next, see where we get to. Okay, pausing and going on again. I'm looking at x minus 1. Then I'm going to write 2x squared plus 1x plus 4. Okay, and hopefully people are okay on that. What do I need to multiply this by? I need to multiply by 2x, gets me 2x squared. 2x times negative 1 is a negative 2x. And I'm going to change my signs and add down. So I'm now looking at 3x plus 4. And I'm going to say that I need to multiply this one by a positive 3. 3 times x gets me 3x. 3 times negative 1 gets me that. Change my signs, add down. I'm now looking at 7. So that's going to be plus 7 over x minus 1. And this one's going to be fairly easy. You just take the integral of that new quotient, and you're looking at, well, that's going to be x squared. You take the 2 and divide by 2 gets you 1, plus 3x plus 7 times the natural log of x minus 1. Okay, then I need to evaluate this by substituting in my 3 and my 5. Yeah, not going to take the time to do that right now. Sorry, guys. I really just don't have the time. Okay, please take a crack then at this one. Okay, this is another way they could write this equation in such a way that it would force you to do the work without actually doing the work. Okay, which of the following are equivalent to that expression there? Well, first thing I'm going to do is try and do the long division on this. So I'm going to say I would multiply this one through by 3. 3 times x is 3x. 3 times 2 is 6. And I change my signs, I add down, I end up with a positive 5. So that's going to be 3 plus 5 over my divisor. So this matches up really, really nicely with that. And notice, I didn't change my bound, so this one's okay. What can they do to make your life miserable? They could change it into a U-bounds problem. Well, how would I go about doing that? Well, it's pretty much just going to be the same sort of thing. They just created, hey, let's let U be x plus 2. Well, does that change anything that I need to do on this problem? Not really. You just have to, come up with the U-bounds. How do I do that? Again, I'm going to say U of 5 is just going to be 5 plus 2 is going to get me 7, and 0 gets me just plain 2. So therefore, this one works also. And last one, and I'll call it quits here. How would I recommend going about doing that? I'm probably just going to distribute this. So I'm going to say this times that, this times that, and see where I'm able to get to. And for the sake of time, that ends up being my answer. So Folks, I don't have time to do any of these. I will try and work those out and post answers sometime later on. Again, apologies for not being there, and hopefully you guys do okay on this.